This video lecture is entitled Riemann Sums and Definite Integrals. Now, the Riemann sum is basically a process that leads to actually evaluating definite integrals. I'm not going to go real in depth in this because I don't ask Riemann sums on exams. Some instructors do, some don't. But I'm going to talk a little bit about it because it's kind of what develops the reason why the definite integral works. Now, the idea behind Riemann sums and approximating area under a curve, which is one of the big applications of what definite integrals are. And the idea is that if you sketch some rectangles under a curve, I'll bring up a quick picture from a section that I don't normally test directly on, but nor will I likely do a video on this either. But so the idea is, let's say if you want to find that area under a curve right here, and if you do it, with some rectangles, you see it doesn't fit exactly, right? Now, the more and more rectangles you have, the less gaps you would have between the rectangle and the curve. And essentially the idea is that if you minimize, you increase the number of rectangles while you're decreasing the width to where you essentially have just a bunch of solid lines that fit right underneath there, and adding up those solid lines would essentially would fit that curve perfectly and would be the right way to evaluate that integral. Now so this formula right here is talking about that's essentially finding the area, because the delta x part is the width of each rectangle, and f of c would be with c of I being any point in the subinterval. F of ci would be your y value, which essentially would be your height of your rectangle, x times y, and this is your summation symbol in front, meaning 1 to n, how many rectangles you have, you add them up, and therefore that would give you your area under the curve. This delta notation here, delta by itself is kind of weird. Delta is usually used as a mathematical operator. Well, anyway, so we come down here, and this delta x, the width of the rectangle, is essentially, you're going from point A to point B. Bring back this other thing for a second. You see here's A to B. So B minus A tells you the width, distance between the points, and then divide it by the number of rectangles, and that will tell you then the width of each rectangle. So, for example, if you were going from 1 to 5 for x, that's a bit 4, and you had 8 rectangles, 4 divided by 8 would be 0.5, so the width of each rectangle would be 1/2. And come down here. So the definition of a definite integral says that the limit of the Riemann sums over those partitions would actually give you the definite integral. Now this thing's called the norm, this delta triangle, or this measurement with the triangle thing here, norm. So you're saying what's happening is, like I was saying earlier, that's saying the width of the rectangles is going to 0 as you are increasing the number of rectangles at the same time. So they're getting narrower, and there's more of them to make it fit the curve perfectly. So this process then, that yields to this definite integral right here, right there. I talked about in a previous video that, indefinite integrals are the ones where you don't have anything there, where the a and b are. Definite integrals is where you have these values a and b. And the a is called the lower limit of integration, and the b is the upper limit of integration. And we'll talk more about that later. Now let's just take a look at this theorem that says continuity implies integrability. I got that right the first time. It's a miracle. If a function f is continuous in a closed interval, then f is integrable on the closed interval a to b. That means the definite integral exists. Let's bring it lower so we can see that. There we go. Like, for example, this particular definite integral, even though we haven't learned how to do this yet, -3 to 3 for the function 1 over x squared dx. Even though once you see how to work these out, you actually can work these out, but it would be wrong to do so. Because 0 is a discontinuity in that interval -3 to 3, which means you do not have continuity all the way across your interval. So therefore, it's wrong to even do it. It means it's, in fact, that's actually called an improper integral, which is something that's discussed in Calculus 2. All right, now, this next part, I'm not going to go through the full details of this, mainly because I'm not asking you to do it for exam purposes. If I was expecting you to do this on a test, I would absolutely thoroughly explain this in more detail. So they're just using this limit definition to evaluate this definite integral from -2 to 1, 2x dx. And the irony is you're going to see how so much simpler this is by using an antiderivative process coming up in the next section. So, but I guess it's, some people like to show the theoretical reasons of why it works. I guess an example of this would be, it's kind of like when you see the definition of a limit, using that limit definition to find the derivative. Yeah, that's good. It shows how the theory is developed and everything. But obviously, you would not want to use the limit. Now that you know the shortcut rules, you would not want to use the limit definition to find the derivative of x squared, obviously. And that's kind of what's happening here. This is the theoretical process that just validates what we're going to do in the next section being correct. Okay, so we're going from -2 to 1, which means we have a distance of 3, and they're dividing it into equal subintervals of n. N is just n here. There's no value for n. We're going to let it approach infinity. So we have 3 over n. So 1 minus a minus 2, 3 over n. Now the CI is the right endpoint of each subinterval. So each CI, as you move along here, obviously the CIs are increasing as you're going from left to right. So it's the A, the starting value, plus whatever I is, the width, or whatever position you're in, times delta x, which is right up here, the 3 over n. So you have -2, basically, plus this. So the I is just I, 3i over n. So they're evaluating the definite integral from that definition we saw up there earlier. Zoom in a little more on this. There we go. This is these two things are the exact same thing. I had that written in red earlier in my notes. That norm going to 0. Yeah, they call it norm right there. Norm going to 0 is the same thing as n going to infinity. And that's basically adding up your rectangle, area of your rectangles. All right. Now, so the function here you see is 2x. And x is essentially represented as this right here. Each CI value is your x. So it's -2 plus 3 over IM. That's each x. So so you're taking the 2x. The 2 is from the 2x. There's your x right there. And then the 3 over n, that's your delta x right here. So we have all this multiplied together as I goes from 1 to n, however many n rectangles. Now, because this summation right here is based on I, That's what's being affected. N is not really affected by what I is. So what they've done, so they've taken the 2 times 3 over n. That's why it's okay to pull that 6 over n to the outside, because I is really the variable here. But you see, so nothing moves here, because there's the I. Now, let's see what happened. Well, essentially that means, though, the sum of 1 to n would just be n, so it makes it negative 2n. Now, what's going on here? Yeah, so it's negative 2 times n would be adding up from 1 to I to 1 to n for negative 2. Now, right here is this little formula I have written over here to the right. And there's other ones for like I squared and stuff like that, which if I was going to actually expect you to do this, I would, show more of that. So the summation, I, 1 to n, meaning if you want to add a list of numbers from 1 to n, it can be represented as n times n plus 1 divided by 2. So there's what happened there. The summation of the I became this. So if you wanted to, impress your friends or something, and you wanted to say, hey, I can add 1 to 100 faster than you can. 1, 2, 3, 4, 5, 6, 7, all the way to 100. All you got to do is go 100 times 101 divided by 2, and you're finished. Pretty convenient. So now we have all n's, and the limit as n goes to infinity, which we've seen, we've done infinity limits in an earlier section. Limits at infinity. So now they took the 6 over n, and we just distributed, so the n's cancel. You have negative 12. And then this gets a little messy here, but if you go n squared plus n, so you have 6n times 3n times n squared over 2. So the n's would cancel. 6 times 3 divided by 2 is 9. But then with this one, you're going to have n times 1 over 2. You have n over 2, which cancels here. It leaves it 3 over 2, because the n's will cancel. 3 over 2 times 6 over n gives you 9 over n. And of course, the limit as n goes to infinity, just like it would be for x, of 9 over n, that goes to 0. So that zeroes out. You add these two, and you get the value as negative 3. Now, as it mentions over here, we'll see more about this, when you evaluate a definite integral, the answer can be either positive, negative, or 0. However, if the problem is supposed to be defining area, you must get a positive result. So there's some modifications to make this work right. Now, of course, we're not going to do it with the rectangles. We're going to do it differently. But obviously, the area of those two triangles over here, obviously is not negative. The reason why it's causing a negative answer, I'll just tell you that, is because being under the x-axis is the bigger area. But actually, I'll just tell you right now what would happen when you evaluate this. You have to do these two areas separately and make sure that one's positive, and then you add them both together. So the answer is not positive 3; it would be something else. Okay, so like I said, we'll see a much better way to do this. Now they are defining the definite integral as the area of a region. So that's one of the big features of what integration is used for. If f is continuous and non-negative on the closed interval from a to b, the area can be represented as the definite integral from a to b of f of x dx. And that's it. And you'll see when we learn how to calculate these that not going to go through that limit process like I showed you in that last example. Now in 7.1, you can modify the calculus a bit to make it do stuff, weird stuff like you have two different curves, up and down, below, above and below, stuff like that. We can make that work to get the right area. But if the graph is above the x-axis all the way between 2 points A and B, it's just this straight up right there formula, just like that. No modifications or anything required. Like I said, we will learn how to evaluate this earlier, but I put in this function x squared plus 3x plus 2. I graphed it. I drew the lines 1 to 3 representing the limits of integration. Started at 1, started at 3. I could have started anywhere there, 0 or whatever, but you clearly see that that's above the x-axis. So it satisfies those conditions. So therefore the area of that region would be this definite integral 1 to 3 of that function. Actually, yeah, this, as an integral, this is actually a difficult problem. It requires Cal 2 technique. But as a geometric problem, it's not too bad, because if you graphed y equals 9 minus x squared from negative 3 to 3, you certainly don't need calculus to do this, because you're just looking at a half circle. So the circle has a radius 3, and I'm sure you recall the area of a circle is pi r squared, but we have half a circle, so it's half of that. So that would be 9 pi over 2. But actually the calculus for this one is a bit involved. But geometry-wise, it's pretty easy. Now we have properties of definite integrals. Two special definite integrals. If f of x is defined at a, of course, we don't have an interval here because it's the same number. From a to a, the definite integral from same number, lower and upper, would always be 0. So like this one, even once we learn how to work it out, we wouldn't need to work it out because the lower and upper limit are the same, therefore it's 0. And another way you can think about it is if you thought about it as being the area between 6 and 6, there'd really be no area there, would there? Because there's no gap in the x's. All right, this is an interesting property. I like to use this all throughout calculus whenever it comes into play. Not because I have to, but this is a good property. So this just says that, and this will make sense later why this is true. But go ahead and just go with it for now. A to B, the definite integral from A to B, if you reverse the A and the B, that creates a negative sign. So like this example, 1 to 3 of f of x dx would be the negative of 3 to 1 of f of x dx. You might be wondering, why would you do that? On purpose? Like I said, we need to know the property just for some questions we're going to see here in a minute, but why would I do that on purpose? Well, some problems you'll see coming up later that are going to have negative signs in them, and I like to do that because if I've got a negative there, if I create a negative, that will kill a negative I have there, because negative times negative, of course, is positive. And I just always find, doing the arithmetic, the fewer negative symbols, the better. But you could still get the problem correct without doing what I'm saying there. But I just like getting rid of any extraneous negatives if I can. All right, this is the additive interval property. So you see this picture over to the right. And I think this is pretty straightforward, just from looking at the picture, that region from A to B could also be found as the region of A to C, the definite integral from A to C, plus C to B. Add those two together and make this. Same thing down here. In fact, for this one, the bottom one, you would have to do it that way because it's hitting the x-axis and changing directions there. So you would have to evaluate it as two separate pieces and add it together. The first one you wouldn't. You don't have to do it that way. So here's an example of a property. So from 2 to, I just chose 4 as an arbitrary point between 2 and 7. Could have chosen something else. But from 2 to 7 will equal from 2 to 4 plus 7 to 4. All right, here comes some more properties of definite integrals. Now these two properties are exactly the same as they were for indefinite integrals, meaning that if you have some k's representing k, c, something we've talked about this, very important. So dx is, that means x is your variable of integration. That means any x you had in here could not be pulled out. The k is essentially representing a constant here because it's not your variable x. So you can pull that k out of there if it's multiplied, but you could not pull any x. And we've seen this one before, adding and subtracting two or more. Actually, it's not just two of them, but two or more, if they're all added and subtracted, can be treated individually if you wanted to. Preservation of inequality. This one's not that big of a deal. I guess the second one's maybe a little interesting, but so if your graph is integrable and non-negative, meaning it's either touching the x-axis or staying above the x-axis, then that just means your definite integral is going to be positive, or also non-negative, I should say. Because I guess the only way it could actually be zero is if your function was y equals 0, the x-axis. All right, that's not that big of a deal. This one says that, I think this one makes pretty good sense here. So you can see the actual proof of this, but not worth our time to look at the proof. I think we can kind of visualize this one pretty easily. So this says f of x is less than or equal to g of x. I kind of made them sort of touch there at that point. Well, pretend like they touch, it doesn't look like it. As long as g didn't dip below f. So if g is above f, that means the definite integral from a to b of f of x dx would be less than or equal to, and the only way it's going to be equal is if f and g are the same function, a and b, from a to b of g of x dx. And so I just drew a picture there, let them touch once. But I think that makes a lot of sense because you would see if you did the area, and you shaded it all the way up to g, you can see there's more area than if you shaded up to f. So therefore, if there's more area, then the definite integral would certainly be larger. All right. That's not too critical. Alrighty, using some properties. Now they're giving us these bits of information up there to solve these problems. I won't read all these out. I'll let you read. Look at, there we go. Just kind of point at them. So we have this definite integral. So first thing I can do is split it into three pieces with 10, 4x, and negative 3x cubed. All going from 2 to 4. They have to go to 2 to 4 if we're using these rules up here. So that was one property I used. I just used another property. I pulled the 10 outside, pulled the 4 out, pulled the 3 out. Now, in the original definition of the problem, it's telling you the definite integral from 2 to 4 dx is 2. So I'll put 2 right there. So it's 10, and the 10 is still there, of course. 10 times 2. The next one, the definite integral from 2 to 4 of x dx, 2 to 4, would be 6, as given right here. So the 4 times 6, and then the definite integral x cubed 2 to 4 is 60. 10 times 2, 4, 6, minus 3, 6 times 60, and that works out to be negative 136. All right. Now, these are interesting. I like these kind of problems. Now, the kind of uses the additive integral, uses a little bit of all the properties. Now, this is the way this little chart, I just draw it this way. It's not like a process where you have to do it that way. I find it to be easier to organize things. Different instructors might show this different ways. So I'm just pretending like that's a number line down there, and I just kind of put those sections there to kind of group it. So it's telling you the definite integral of from 0 to 3 f of x dx is 4, and 3 to 6 f of x dx is negative 1. So what I did is I went over here and I just wrote from 0 to 3 and 3 to 6. We have the additive integral property. So I'm just writing from 0 to 3. I'm just placing that value 4 right there. It's given right here. And I'm placing the value 3 to 6, area being negative 1 right here. And it wants us to find these 4 results. I think we can do that. Okay, so it wants 0 to 6. So using that additive property we saw earlier, is that 0 to 6 would be the same as 0 to 3 plus 3 to 6, which I have right up here. So 0 to 3 is 4, 3 to 6 is negative 1, so 4 plus negative 1 is 3. Now, 6 on bottom, 3 on top. All right, we'll use that negative rule. That if 6 on bottom and 3 on top, I can reverse the 3 and the 6, but that creates a negative sign. So by definition, 3 to 6 is negative 1. So with a negative in front, negative of negative 1 would be 1. And the next one, 3 to 3. Okay, super simple there. If you know that property, upper and lower are the same. Answer is automatically 0. Now the next one, we have a negative 5. And so I pulled the negative 5 out. So now we have negative 5 outside. Now it's 3 to 6. So we know the 3 to 6 by definition up here is negative 1, but you have to keep the negative 5 there. So it's negative 5 times the given negative 1 originally makes positive 5. All right. Here's another one. All right, so it's a little bit different here. I like this one too. It gives you negative 1 to 1, and it gives you 0 to 1. So I drew a negative 1 to 1, and then I labeled this whole thing negative 1 to 1 being 0. Don't confuse this blue 0 with that red 0. That's why I put equal 0, because it's that 0 right there. And then 0 to 1 is 5. So that's given. So the two things that are blue here are the given values. The green one I found. Now let's see, how did I get the negative 5? All right, well, I used the fact that that from negative 1 to 0 plus 0 to 1 would have to be whatever negative 1 to 1 is. So if that's 0 and 0 to 1 is 5, therefore negative 1 to 0 has to be negative 5, because negative 5 plus 5 would be 0. All right. So that was a little bit trickier then. So it gave you the full length and then one of the sub partitions there. And, so negative 1 to 0. Okay, that's the one I kind of already found right there, knowing it had to add up to 0. And so there we go. So this one's so it's 0 to 1 minus negative 1 to 0. Okay, 0 to 1 is 5. Negative 1 to 0 right here is negative 5. But be careful here, it says minus between the two. So don't add those and get 0. If it would have been a plus there, then it would have been 0. Well, that just would have been this right here. But 5 minus a minus 5 would be 10. And negative 1 to 1, you see that's given as 0. So even with that multiplier 3, 3 times 0 would be 0. And the next one, 0 to 1, and with 3 times 3f of x. So 0 to 1 we know is 5, but the 3 multiple means we multiply by 3, so 3 times 5 will be 15. And that concludes this video on Riemann sums and definite intervals.